Hey you all, this is Dr. Habib Ahmed and I welcome you to my YouTube video exploring the fascinating world of multi-junction solar cells. Multi-junction solar cells are advanced photovoltaic devices and they are like the superheroes of solar panels which can capture sunlight with incredible efficiency. Multi-junction solar cells have a unique structure which consists of multiple semiconductor layers stacked on top of each other. Now if you talk about the simplest solar cell, in a simplest solar cell we have a p-type layer and we have an n-type layer, and that would be a single junction solar cell, or you can call it a single cell. However, in a multi-junction solar cell, consider this example where we have multiple cells. We have an indium gallium phosphide top cell, and then we have a gallium arsenide based middle cell, and then we have a germanium based bottom cell. Each cell has a p-type layer and an n-type layer, and these cells are connected together with the help of tunnel junctions, and I'm going to talk about the significance of tunnel junctions slightly later. So in this example we have three cells. We call it a triple junction solar cell. Similarly, we might have dual junction solar cells and so on. The advantage of multi-junction solar cells is that they capture sunlight more efficiently as compared to the traditional solar cells. Now, how do they achieve this? Well, it's all about the layers. Instead of relying on a single layer of semiconductor material to convert sunlight into electricity, multi-junction cells incorporate multiple layers, each optimized to absorb a specific range of wavelengths. Now, if you have watched my theoretical lecture on solar cells and also my Silvaco TCAD simulation videos on perovskite solar cells, silicon, gallium nitride based solar cells, gallium arsenide based solar cell, you might know that each solar cell has a spectral range where they have a lower cutoff wavelength and an upper cutoff wavelength. So let me open a particular presentation in this regard. So we know that a solar cell has a particular spectral range where the upper cutoff wavelength depends on the band gap of the semiconductor according to this formula, and the lower cutoff wavelength depends on the absorption coefficient of the material of the semiconductors which actually make the solar cell. Then the penetration depth of light is equal to 1 over the absorption coefficient. So like shorter wavelength lights, we talk about UV light, they can actually travel shallower into the semiconductor. On the other hand, longer wavelength light, for example, if you talk about red light in the visible spectrum, or we can talk about the infrared light, they can travel deeper into the semiconductor layers. So once again, the lower cutoff wavelength is dictated by the absorption coefficient, and the upper cutoff wavelength is dictated by the band gap of the semiconductor. Now, based on that concept, we can deduce that shorter light can travel shallower into semiconductors. Medium wavelength light can travel up to medium distances inside semiconductors, and longer wavelength light can travel deeper into semiconductor materials. So with that concept in mind, if we go back to the multi-junction solar cells, here looking at the structure, we can conclude that since in this structure the indium gallium phosphide based cell has a wider band gap, like the band gap of gallium phosphide is 2.26 electron volts and the band gap of indium phosphide is 1.35. So based on the indium content and the gallium content, the band gap of the indium gallium phosphide would be somewhere in the range of 1.35 to 2.26 electron volts. consider it as, for example, 1.9 electron volts or 1.8 or 2 electron volts. We can tune it that way. So the highest energy photons, or conversely you can say that the shortest wavelength photons would be absorbed inside the top cell. Similarly, if we talk about the middle cell, if it is based on gallium arsenide, the band gap of gallium arsenide is 1.4 electron volts. So the medium wavelength light is predominantly going to be absorbed inside this cell, while the bottom cell is based on germanium, which has a band gap of 0.67 electron volts approximately. So the longer wavelength light is predominantly going to be absorbed by the germanium cell. Similarly, we might have other configurations. We might have quadruple junction. We can design it that way as well. And we can have dual junction solar cell as well. So we have to optimize the individual cells in such a way so that we can absorb the maximum light from the solar spectrum in order to achieve the maximum efficiency. And we need to consider like couple of other parameters in the design considerations as well. We are going to talk about them later. One common type of the multi-junction solar cell is a dual junction solar cell. So already discussed the Silvaco TCAD simulation of single junction solar cells. Now let us, in this lecture, I am going to talk about the Silvaco TCAD simulation of a dual junction solar cell, which as the name suggests has two distinct layers. The top layer of a dual junction solar cell is typically made up of semiconductor material optimized to capture shorter wavelength sunlight, or in other words you can say high energy photons, for example blue and green light. So I'm going to talk about this structure is slightly different from mine, but once again it has two cells. The top cell is based on indium gallium phosphide and the bottom cell is based on gallium arsenide, similar to the structure which I'm going to simulate today, which has a similar configuration. So the top layer, since it's going to have a wider band gap, the top cell is going to absorb shorter wavelength light such as blue light and green light, while the bottom layer, the bottom cell, is going to capture longer wavelength sunlight, including yellow light, orange light, red light and infrared light. And this layer can consist of materials, for example silicon, but in my case I have chosen gallium arsenide as the bottom cell. So by dividing the solar spectrum between these two subcells, a dual junction solar cell can achieve higher efficiency as compared to the traditional single junction solar cells, where the top layer captures the high energy photons while the bottom layer captures the low energy photons, maximizing the overall energy conversion efficiency of the multi-junction solar cell. So we are gonna dive deeper into the science behind the dual junction solar cell with the help of simulations, and we are going to learn about this innovative technology driving the solar energy forward. So stick around and join us for this enlightening journey. So I have already created a code in this regard, but since we all know that the font size in the deck-built environment of Silvaco TCAD is not really large, so a lot of times, then some of my followers, they complain about either they are not able to see the coding, the program, because of resolution issues or because of poor internet connection. So what I've started doing is I've copied the program or the Silvaco TCAD for this multi-junction solar cell into a Microsoft Word document. Let me walk you through this document. We start with GoAtlas, and then I perform meshing. I'm not going to go into the details of the meshing. However, I'm going to skim through the meshing. So my structure is running from 0 to 1 micrometer in the x direction, and from 0 to, you can say, 3.55 micrometers in the y direction. Let us look at the structure as well. Here is my structure running from 0 to 1 micrometer in the x direction, and from 0 to 3.55 micrometers in the y direction. And I have performed the meshing in such a way. So in order to see the meshing, I right click on the structure, go to display, and then click on this meshing icon, hit apply, click OK. I performed the meshing in such a way that I have included denser meshing for thin layers, and also I have included a denser meshing for interfaces, and included sparser meshing for bulk regions, for bigger regions, and for regions where we don't have the interfaces. After the meshing, I have included the individual layers of the dual junction solar cell. My first layer is based on indium aluminum gallium phosphide. So as I already discussed, that the band gap of indium phosphide is 1.35 electron volts, and the band gap of gallium phosphide is 2.26 electron volts. For the indium aluminum gallium phosphide layer is called the top window layer. We need to include the top window layer. It is typically like made up of a transparent conductive material, and this material allows sunlight to pass through the structure through the top layer with minimal absorption or reflection, ensuring that a maximum amount of light reaches the individual subcells where energy conversion occurs. So if we look at the structure once again, this blue layer at the top, which you can also notice from the color legends, represents the indium aluminum gallium phosphide layer. We can zoom in on the structure to see this layer, and from the structure you can see that the thickness of this layer in the y direction is 0.03 micrometers, or in other words you can say that it's 30 nanometers. So for the indium aluminum gallium phosphide, the top window layer, this layer is running from 0 to 1 micrometers in the x direction, and from 0 to 30 nanometers in the y direction. Its x component is 0.371, and its y component is 0.159. And now let me tell you what that means. So I went to the Silvaco TCAD Atlas manual, and from there, if you look at the description of the x and y component for the indium aluminum gallium phosphide layer, so x over here represents the aluminum content. So like in this indium aluminum gallium phosphide layer for the dual junction solar cell structure, I have included 37% aluminum. Similarly, y represents the gallium content or the gallium composition for this layer. So the gallium composition is approximately 16%. So if you add 37 plus 16, it becomes 43 plus 10, 53%. Now the indium content then becomes 100 minus 53 is equal to 47%. So here is the description of these individual components for the indium aluminum gallium phosphide layer. Now as I already discussed, that the purpose of the top window layer is to allow maximum amount of sunlight to reach the individual semiconductor layers where the energy conversion occurs. So this top window layer serves as a transparent layer for the transmittance of light into the individual subcells, but also it needs to be heavily doped so that it acts as an electrical contact. In addition to being transparent, the window layer acts as an electrical contact between the semiconductor layers and the external circuit. It enables the flow of electrons generated by the absorption of sunlight, thus completing the electrical circuit necessary for power generation. So here is the description of the thickness and composition of the layer, and as far as the doping of this layer is concerned, I have defined the doping somewhere else later down in the code. This is my region number 1, and I have introduced a whole concentration of 2 into 10 to the power of 18 per centimeter cube for the top window layer, which is the indium aluminum gallium phosphide layer. Also, if I right click on the structure and hit display and click on this icon which should display the electrodes, hit apply, we see that my top electrode is anode and the bottom electrode is cathode. So since I have introduced the top electrode as the anode, I have doped the top window layer, the indium aluminum gallium phosphide layer, as a p-type doped layer with a whole concentration of 2 10 to the power of 18 per centimeter cube. Then after the top window layer, we have the top cell, as you can see over here from the color legends as well. We have 2 layers. This let me zoom in on on the top cell based on indium gallium phosphide. This is a thin layer which is p-type doped, and then we have a thicker layer which is n-type doped. This thin layer which is p-type doped should be heavily doped, and it's called the emitter layer. And this thicker layer which is n-type doped, it's thicker as well. This should be slightly lightly doped. The purpose of this layer is called the emitter layer, and this layer is called the base layer. The emitter layer actually absorbs the sunlight, resulting in the generation of electrons and holes, and then the base layer is lightly doped, but it should be conductive as well. So its doping and thickness should be optimized, and the purpose of this layer is to enable the carriers to flow to the bottom subcell, to the back surface field, from that point onwards to the tunnel junction into the bottom subcell. So you can say that the base layer actually facilitates the collection or extraction of carriers. Now let us go back to the code. Region number 2 is indium gallium phosphide based, running from 0 to 1 micrometers in the x direction, and from 30 nanometers to 80 nanometers in the y direction. And region number 2 has a doping concentration of 2 10 to the power of 18 per centimeter cube, p-type. So it is p-type doped. You can say its whole concentration is 2 10 to the power of 18 per centimeter cube. So if we talk about this layer, this thin layer, its thickness is 50 nanometers, and it has a whole concentration of 2 10 to the power of 18 per centimeter cube. We call it an emitter layer. Similarly, region number 3 is also indium gallium phosphide based, and its carrier concentration is 7 10 to the power of 16 per centimeter cube, and it's running from 80 nanometers to 630 nanometers in the y direction. So as you can see that this layer is relatively thicker. The base layer is much thicker as compared to the emitter layer, and I already discussed the reasoning for that purpose. Now if you look at the code, we see our X component is 0.49, or you can say it's 49%. What does that mean? Once again, if you go back to the description of indium gallium phosphide layers, and if you consult the Atlas manual of the Silvaco TCAD for this purpose, you might see that X over here represents the gallium content. So like in this case, my X component is 49%, which means that here I've included 49% as the gallium content and 51% as the indium content. Now let us talk about region number 4. My region number 4 once again is indium aluminum gallium phosphide based, and I already discussed the significance of the X component and of the Y component over here. It's running from 630 nanometers to 660 nanometers. So you can see it has a thickness of 30 nanometers. This light blue layer over here, it has a thickness of 30 nanometers, and it is based on indium aluminum gallium phosphide material. The significance of this layer is that it's called the back surface field, and it is a key component located on the back surface of the cell. So our cell is based on indium gallium phosphide. We have the p-type gallium phosphide, indium gallium phosphide, and then we have the n-type indium gallium phosphide, which is the top subcell. So, and it's located at the back side of this top cell. So that's why it's called the back surface field. Its primary purpose is to improve the efficiency of the solar cell by reducing the recombination losses of charge carriers, particularly minority carriers at the back surface of the top cell. The back surface field layer is typically heavily doped with impurities to create a high concentration of charge carriers near the back surface. So because of this high concentration of the charge carriers, it creates a built-in electric field that repels minority carriers, such as holes in an n-type semiconductor. Like this layer is n-type, so it's going to repel holes from this layer, preventing them from reaching the rear surface and recombining with carriers of the opposite type. So the back surface field is a critical component. I mean, every layer is critical. You need to care about the doping concentrations, you need to care about the thicknesses, and this is the significance of the back surface field. So region number 4, let's also look at the carrier concentration of this layer. Region number 4 is n-type, and its electronic concentration is 2 into 10 to the power of 18 per centimeter cube. Now let's go back to the layers description. Now we have the tunnel junction. As you can see, my top cell is based on indium gallium phosphide, and the bottom cell is based on gallium arsenide. And the tunnel junction actually connects the two subcells with each other. Now, a tunnel junction plays actually a really crucial role in facilitating the flow of charge carriers between adjacent semiconductor layers, while maintaining a high voltage across each junction as well. And it's really significant. It serves different purposes. So before talking about the significance of the tunnel junction, let's talk about the description of these two layers. In a tunnel junction, we have a heavily doped n-type layer and a heavily doped p-type layer. These are my layers number 5 and layer number 6 based on gallium arsenide. So layer number 5 is based on gallium arsenide, and it's running from 660 to 685 nanometers. Then layer number 6 is gallium arsenide based, and it's running from 685 to 710. So the thickness of these two layers is 25 nanometers each, and the carrier concentration of these two layers is, the top layer is n-type, the bottom layer is p-type. with subsequent carrier concentration of 5 10 to the power of 19 per centimeter cube and 3 10 to the power of 19 per centimeter cube. So these layers need to be heavily doped in order to form a tunnel junction. In a tunnel junction, instead of the thermionic emission, instead of carriers flowing over a barrier, the carriers actually tunnel directly from the conduction band of one layer to the valence band of the other layer and vice versa. This tunnel junction serves a few purposes. So these two green layers, the thin layers, which have thicknesses of 25 nanometers each, they serve a few purposes. One, they make a series connection between the top cell and the bottom cell. As you know, their multi-junction solar cell consists of multiple semiconductor layers, where each layer is optimized to absorb different portions of the solar spectrum. So to efficiently extract the electrical current, these layers need to be electrically connected in series. However, each layer operates at a different voltage, so a direct electrical connection between them would lead to a short circuit, resulting in zero open circuit voltage. So a tunnel junction is necessary here, which provides a low resistance series connection between the two layers while maintaining a voltage difference required for efficient energy conversion as well. Secondly, it provides carrier transport. The tunnel junction allows charge carriers, both electrons and holes, to tunnel through it, enabling them to move from one semiconductor layer to the other. And this facilitates the flow of current between the junctions without significant losses, ensuring that the electrical power generated by each layer contributes to the overall output of the solar cell. Third, it serves as it provides voltage matching, which is a critical aspect of multi-junction solar cell. So each semiconductor layer in a multi-junction solar cell should operate at its optimal voltage for maximum efficiency. And the tunnel junction helps to achieve voltage matching by allowing the voltage across each junction to be independently controlled. And this ensures that the voltage generated by each layer adds up constructively, leading to higher overall efficiency of the solar cell. Fourth, it provides bandgap engineering. Bandgap engineering is really crucial. If you know bandgap engineering, you can design any kind of device. By carefully selecting the materials and doping profiles of the tunnel junction, it is possible to engineer the properties to match the requirements of the adjacent semiconductor layers. This includes, for example, adjusting the band gap and the doping concentration to minimize losses due to carrier recombination and the tunneling resistance. So overall, the tunnel junction is a critical component of the multi-junction solar cell, enabling efficient series connection between the two subcells and facilitating the carrier transport, achieving voltage matching, and contributing to the overall optimization in the performance and efficiency of the multi-junction solar cell. So far we have talked about 6 layers. Let's go back to the code once again. My region number 7 is based on Indium Gallium Phosphide. Once again, the X component in the Indium Gallium Phosphide layer is 49%, or you can say the gallium component is 49%, and the indium component is 51%. This layer runs from 710 nanometers in the y direction to 750 nanometers, or you can say it has a thickness of 40 nanometer. And it has a doping concentration of 310 to the power of 18 per centimeter cube, and it is p-type doped. If we refer to the structure as well, this is this thin layer. It has a thickness of 40 nanometers, and from the color legends you can also notice that this is indium gallium phosphide based, having a high doping of 310 to the power of 18 per centimeter cube. You can call this layer as the middle window layer, and we place the indium gallium phosphide layer over here on top of the bottom cell. The bottom cell is based on gallium arsenide. So we place this middle window layer, or the window layer, on top of the bottom cell, and this is also a crucial layer. By proper choice of the thickness of the indium gallium phosphide layer, we can optimize the efficiency of the solar cell. This window layer plays a critical role in enhancing the efficiency and performance by facilitating the light transmission from the top cell to the bottom cell, by allowing charge carriers to flow through it, and by contributing to the bandgap or effective bandgap engineering of the structure. Bandgap engineering, as I already discussed, is really crucial. So the window layer's material properties need to be carefully chosen to match the energy bandgap of the semiconductor layers. This helps optimize the overall performance and efficiency of the solar cell by minimizing losses due to mismatched band gaps. So like one of the purposes of this layer is to kind of match the band gap of the top solar cell with the bottom cell, ensuring efficient charge carrier transport across the cell. Then we start introducing the bottom cell. Region number 8 is based on gallium arsenide running from 750 to 1250 nanometers, and region number 9 is also based on gallium arsenide running from 1250 to 3250 nanometers, or you can say from 1.250 micrometers to 3.250 micrometers. Let us look at the carrier concentrations of region number 8 and 9 as well. Region number 8, which is also called an emitter layer, absorbing the incoming photons, resulting in generation of electrons and holes, has a carrier concentration of 210 to the power of 18 per centimeter cube. It is p-type doped, while region number 9, which is also called the base layer, is actually it has a carrier concentration of 710 to the power of 16 per centimeter cube, and this layer actually facilitates the extraction or collection of carriers. So this was the bottom cell. Then we introduced two more layers. Region number 10 is aluminum gallium arsenide based, running from 3.250 to 3.350 micrometers. So it has a thickness of 100 nanometers. This lime layer, you can see it is aluminum gallium arsenide based. And as far as the X component of this aluminum gallium arsenide layer is concerned, the X component over here is 0.7. So once again, I refer to the Atlas manual, and from the manual I found out that the X component for aluminum gallium arsenide actually refers to the aluminum content. So this aluminum gallium arsenide layer has 70% aluminum and 30% gallium in the aluminum gallium arsenide alloy. And aluminum gallium arsenide has a band gap higher than the band gap of the aluminum gallium arsenide layer. This layer, which we will later see from the energy band diagram as well, it acts as, so if this layer is p-type doped, this is n-type doped, so this is also n-type doped. This acts as a hole blocking layer. On the bottom side we have cathodes, so it acts as a hole blocking layer, facilitating the flow of electrons to flow towards the cathode, but blocking the flow of holes so that holes can effectively move towards the anode. And then at the bottom, once again, we have the gallium arsenide layer, and running from it has a thickness of 100 nanometers, and the carrier concentration of region number 10 and 11, both of them are n-type doped, and their electron concentrations are 5 10 to the power of 18 and 1 10 to the power of 18 per centimeter cube respectively. Then after defining the regions, I have assigned the anode as the top electrode and cathode as the bottom electrode, and then I save the structure and I start another block of Atlas code where I import this structure which I've saved in the previous block of the Atlas code. From this point onwards, I have actually assigned the carrier concentrations of different layers. And then at this point, we assign the optical properties to different layers used in this dual junction solar cell. So like for example, for gallium arsenide, I'm actually introducing a SOPRA file. SOPRA is equal to gallium arsenide.nk, where n represents the refractive index and k represents the absorption coefficient of the gallium arsenide of the gallium arsenide layer. So we know that our input for a solar cell is light, and we need to include the light properties for the proper simulation of our solar cell. So we need to include the refractive index and the absorption coefficient versus wavelength. We know that the refractive index and absorption coefficient for semiconductor varies versus wavelength. So there are actually files inside Silvaco TCAD, like built-in files. They are named as SOPRA files. For gallium arsenide, we have gallium arsenide.nk, which has all the optical properties information for gallium arsenide. We include that in our code. We also include SOPRA file for indium aluminum gallium phosphide. We include similar file for aluminum gallium arsenide as well. However, we don't have the optical properties of indium gallium phosphide built into our Silvaco TCAD software. So we have to include it manually. And for that purpose, what I've done is I have created a .nk file where I have made 1000 triplet entries. The first column represents the wavelength. The wavelength runs from 0.2 micrometers, or you can say 200 nanometers, to 1.2 micrometers. Similarly, the second column represents the value of the refractive index versus wavelength, and the third column represents the value of the absorption coefficient versus wavelength. So I created this file, and then inside the Silvaco TCAD, I'm actually calling this file with this command, index.file. After that, I've included the electron affinities of indium gallium phosphide and aluminum gallium arsenide. We include different models for the simulation of the solar cell. Then there are several methods for calculating the solutions of semiconductor devices. I've included Newton as a method with the 40 number of iterations and 20 numbers of traps at max. So actually, if there are convergence problems, it gives it a number of tries, reduces the step by half, and keeps doing that until it finds a solution, and the maximum number of times in this code that it can do is 20. Then inside, from the structure files, I want to look at different optical properties, for example, optical intensity, and I also want to see the bandgap, conduction energy level, valence energy level, different kind of charges, electrons and hole mobilities, recombinations, and permittivity, etc. So the output command actually serves that purpose. Then I want to save the structure under thermal equilibrium. So solve initial, solve previous gives us an initial guess about the structure. And after saving the file, I use plot command to plot this file under thermal equilibrium. So this figure that you can actually see over here is actually the structure of my dual junction solar cell under thermal equilibrium. I've included this block over here to look at the IV characteristics of the solar cell under dark conditions. So I created a log file with this name, and then I run a sweep for the anode from 0 to 2 volts with a voltage step of 0.02 volts. After that, I also want to look at the IV characteristics of the solar cell under light conditions. So the first step in the solar cell analysis is to illuminate the device. We need to turn on the illumination, and I would do that under AM 1.5 conditions, which correspond to the standard test conditions. So I include a beam number 1 under AM 1.5 conditions, which are the standard test conditions. As you know, 1000 watt per meter square, or conversely we can say 100 milliwatts per centimeter square at room temperature, 48.2 degrees angle with respect to zenith, or with respect to the vertical direction, and it's originated at minus 0.2 in y direction, so you can say like slightly above the structure, directed downwards. And I use the subtract command because what it does is the last layer, it assumes that it's infinitely large, helping in increased absorption from the solar spectrum. So after assigning these, now we want to initiate, we want to illuminate the device. We want to initiate the beam with the help of solve statement. And here, in some cases, we may encounter convergence difficulties. So we may need to ramp the light intensity instead of giving it just a single value. So initially we have set it to 1 milliwatt per centimeter square, then 10 milliwatts per centimeter square, then you can say 100 milliwatts per centimeter square, and finally to 1. So this would be 1 milliwatts per centimeter. This would be 1 sun. This would be 1 sun. So 1, you can say, kilowatt per meter square. And this would be less, all these would be less than 1 sun. So B1 is equal to 1 is 1 sun, 1000 watt per centimeter square, 1000 watt per meter square. Then it's 100 milliwatt per meter square, 10 milliwatt per meter square, 1 milliwatt per meter square. We create a log file, and then we run a sweep under light conditions from 0 to 2 volts with a step of 0.02. Then we plot the dark log file and the light log file in one plot, and we use overlay command for that purpose. And then I also want to see the structure under light conditions, so I save the structure at this point under light conditions, and then I plot the structure. At this point we need to calculate the figures of merit for the solar cell, for the dual junction solar cell. So I initiate the log file under light conditions once again, and then I use formulas to calculate the short circuit current. We find the short circuit current where the x-intercept is 0. Similarly, I also want to see the short circuit current density in milliamps per centimeter square. So in order to convert it into current density, we have to divide the short circuit current by the area of the device. Now if you look at the device, It's running from 0 to 1 micrometer in the x direction, and the light is incident at the top surface of this structure. Now, virtually this structure also has a third dimension, like the inverse dimension. We can call it the z dimension. And by default, if you don't introduce the thickness of that dimension, Silvaco TCAD sets it by default to 1 micrometer. So you can say this is like this top surface has a 1 micrometer by 1 micrometer area, and then we convert it to centimeters. Let me close this window. And then if you want to convert it to centimeters, so that would be 10 to the power minus 4 into 10 to the power minus 4 centimeter. We divide the current by the area in order to get the current density. So in the denominator, if you have 10 to the power minus 4 into 10 to the power minus 4, 10 to the power minus 8, take it to a numerator, it becomes 10 to the power of 8. And then we want to see the current density in milliamps, so multiply it with 1 into 10 to the power of 3. So this gives you the current density in milliamps per centimeter square. Similarly, we find the open circuit voltage where the y-intercept is 0. Then we want to save the power curve, and we want to find the maximum power point, the maximum voltage, maximum current. Fill factor would be maximum voltage times maximum current divided by short circuit current density times open circuit voltage into 100. Similarly, efficiency would be output power divided by input power. Output power is the product of the maximum voltage and maximum current, and the input power is light intensity times area. Now, the light intensity is 100 milliwatts per centimeter square, and the area is 10 to the power of 8 centimeter, 10 to the power minus 8 centimeter square. So in the numerator, in the denominator, it's going to be 10 to the power minus 8 centimeter square. Take it to a numerator, it becomes 10 to the power of 8 into total into 100 becomes our efficiency. These would give us these different figures of merit. Then I started another block of Silvaco TCAD code, Atlas code. Here I want to determine the spectral range and the internal and external quantum efficiency of the dual junction solar cells. So for that purpose, I included the material properties once again, and I called the structure from the previous block. Moving further, I've introduced the electron affinity properties. I've introduced the beam once again. We want to look at the output parameters. And then finally, we initiate the beam, and finally, I included some formulas for calculating the internal and external quantum efficiency of the solar cell. As we know that, and then I want to plot the internal and external quantum efficiency in the same figure. Finally, we quit the code. So now it's time to run the code. And let me close this figure as well. Close this window as well. It's going to take some time. Here is the structure under thermal equilibrium. Once again, as a refresher, the top layer is indium aluminum gallium phosphide, which has a wide band gap. It acts as a top window layer. Then we have, and this is going to be p-type doped. Then we have a p-type doped indium gallium phosphide layer. Then we have an n-type doped indium gallium phosphide layer. Then we have an n-type doped indium aluminum gallium phosphide layer, which acts as a back surface field. Then we have, if this is p-type, n-type, if this is p-type, p-type, n-type, this layer is also n-type. Then the top tunnel junction layer is also n-type. This layer is then p-type. Then this indium gallium phosphide layer is also p-type. Then we have the bottom cell, This gallium arsenide layer is p-type, the emitter layer. The base layer is n-type. Then this layer, which acts as a hole blocking layer, is also n-type. Finally, we have the gallium arsenide substrate layer also as the n-type. If we click on the structure, go to display, we click on this icon and hit apply, we see the anode and cathode as well in the structure. We are also going to keep an eye on the code. So right now it's running at the illumination phase, where the beam is like 1 milliwatt per meter square right now. So it's going to keep running. Let us look at the energy band diagram of this structure. Energy band diagram, energy band gap engineering. Band gap engineering is really crucial. So in order to look at the energy band gap of this structure, we go to tools, then cut line. So I'm going to draw a cut line across the entire structure. Well, before that, let us look at the meshing. So in order to look at the meshing, we right click on the structure, click on display, and then click on the meshing icon. So as you can see, the meshing is denser in the thinner regions, also at the interfaces, but it's sparser in the thicker regions away from the interfaces. And this is crucial. Like, if you don't define the meshing in a proper way, you might not get the desired results from your simulation. So now I disable the meshing once again. We go to tools, cut line, and here I draw a cut line across the entire structure. And let me full screen this one. So this figure on the right, actually initially it's giving me the absolute net doping. As we know that the top layer has a doping of 2 to the power of 18, and then we have other layers with the, and then this layer also has 2 to the power of 18, this layer has 7 to the power of 16, and so on. We already discussed that. So I want to see like the energy band diagram, and also the energy band gaps of different layers as well. So let us look at the energy band gaps of different layers initially. If you look at this figure, for the indium aluminum gallium phosphide, the band gap is, we can zoom in on this, is approximately 2.335 electron volts. So it is a wide band gap layer. Why do we keep it wide band gap? Because the purpose of this layer is to allow the light to pass through the top layer into the following subcells, the cells which result in the generation of the electron hole pairs. And secondly, it needs to be heavily doped so that it serves as a conductive electrode as well, facilitating the transport of carriers to the external circuitry. Then we have the top subcell, which is based on indium gallium phosphide, and for this layer the band gap is approximately 1.875 electron volts, or you can say 1.88, close to 1.8 electron volts. Then once again we have the indium aluminum gallium phosphide layer having a band gap of 2.335 electron volts. Then we have the gallium arsenide based tunnel junction, and as you can see over here, its band gap is close to 1.42 electron volts. Then we have the indium gallium phosphide layer once again, and its band gap is close to 1.9 electron volts. And after that we have the gallium arsenide emitter and base layers with a band gap of approximately 1.42 electron volts. Then we have the aluminum gallium arsenide hole blocking layer, and its band gap is approximately 2 electron volts. And finally we have this layer, the gallium arsenide layer, which has a bandgap of 1.4, close to 1.42 electron volts. Let us see the progress of our code. So right now it's running the IV characteristics under light conditions. We are at 1.76, 1.78, 1.8 electron volts. It's almost there. Before that, let us quickly look at the energy band diagram. So tools, cut line. I'm gonna draw a cut line across the entire interface, and here I go to display, and then I want to see the conduction energy level, valence energy level, electron quasi-Fermi level, hole quasi-Fermi level. Hit apply. We can disable the hysterics. So you can see the energy band diagram. Like this layer over here is the indium aluminum gallium phosphide layer, the top window layer. And as you can see, it acts kind of, it's going to act, we will see it under light condition. It acts as a as an electron blocking layer because we have a high barrier for electrons over here. Then this is the top indium gallium phosphide subcell. Then we have the tunnel junction and the bake surface field and the indium gallium phosphide window layer. And then we have the bottom gallium arsenide based bottom subcell for the dual junction solar cell. This is the aluminum gallium arsenide layer. As you can see that it provides a barrier for holes. So this aluminum gallium arsenide acts as a hole blocking layer. And finally we have the gallium arsenide layer. At this point, we already simulated the IV characteristics of the solar cell under dark and light conditions. So the red curve is for dark conditions and the green curve is the IV characteristic of the solar cell under light condition. And as you can see, the y-intercept for this IV characteristic is approximately 1.74, which is going to be the open circuit voltage for this dual junction solar cell. Similarly, the short circuit current is approximately 1.3 to 10 to the power minus 10 amps. From here we can extract the short circuit current density, and also we can extract a lot of other parameters. Also we can look at the power curve, and if you look at the power curve, we see the maximum power point, which is around 1.54 volts, and we can see the maximum current as well for this maximum power point. Let me close this as well. We can look at these figures of merit over here by clicking on this icon. So in order to see these performance parameters or the variables which we have included in our code, we click on this icon. So here we see the short circuit current. The short circuit current density is approximately 13.25 milliamps per centimeter square. Similarly, the open circuit voltage is approximately 1.74 volts. Here is the maximum power, the maximum voltage, the maximum current. Our fill factor is 86.6, which is incredible, and our efficiency from this dual junction solar cell is approximately 20%, which is good as well. We can also look at some other things, like this is the structure of the dual junction solar cell under light conditions. So in this structure, if I right click on the structure and go to display, and then I go to contours, click on contours, like enable it, go to define contours, and if I look at the photo generation rate, we see the photo generation rates inside the structure. So the photo generation rates are generally high, like in the emitter layers, in both the top subcell and also in the bottom subcell. We can also see the photon absorption rate in this structure. If we go to the log file, we get a better idea of it, and we can also draw a cut line across this structure to look to see the photon absorption rate. So here is the photon absorption rate versus depth for the dual junction solar cell. Similarly, we can right click on this to look at the photo generation rate as well. So from here you get a good idea of where your maximum absorption is occurring, where your absorption is lower, and that kind of stuff, where your transparent layers are. Like this layer over here, it acts as a hole blocking layer, but it's not absorbing a lot of photons. This layer over here is the indium gallium phosphide window layer. So it's kind of transparent to the bottom subcell, and it serves a lot of purposes that we already discussed. One crucial point to mention that needs to be noted in let me disable the contours. One crucial point in designing a multi-junction solar cell is current matching in a multi-junction solar cell. That is really crucial because it's a tandem solar cell where you have multiple subcells connected in series. So the net current from this structure would be the current that is achievable, the minimum current achievable from any of the subcells. So we need to perform proper current matching of the individual subcells. And how do we perform the proper current matching? It's based on two design parameters. The thicknesses of the individual layers are crucial, and we need to understand the absorption capability of the individual layers as well. So for example, if the absorption coefficient of the bottom subcell is lower as compared to the top subcell, we need to increase the thicknesses of these layers in order to achieve increased absorption from this bottom subcell, and in order to match the current capability of the bottom subcell with the top subcell. So current matching is really crucial. Finally, I can also show you the spectral response of this solar cell. So we click on optical wavelength, we hit apply. So the spectral response range of this solar cell is, you can say, from like 100 nanometers to, you can say, 1 micrometer, or maybe up to 1.2 micrometers wavelength, or up to 1200 nanometers wavelength. Similarly, we can see the internal and external quantum efficiency. The red curve represents the internal quantum efficiency. The green curve and the blue curve represents the external quantum efficiency. The blue curve also takes into account the absorption from in the solar cell, losses due to absorption in the solar cell. We know that the external quantum efficiency is lower as compared to the internal quantum efficiency in solar cells because of several reasons. Because of incomplete absorption based on the upper cutoff wavelength criteria and the lower cutoff wavelength criteria, based on recombination mechanisms, for example, Shockley-Red Hall recombination, OJ recombination, these kind of recombination mechanisms, because of reflections from the top surface, etc., and because of so many other different kind of reasons. So that concludes this YouTube tutorial for today, and I'm still trying to understand triple junction and quadruple junction solar cells. It's going to be a good challenge for me to optimally design quadruple junction and pentuple junction solar cells. I hope this video was really informative for you. I think it's good stuff. It's research level stuff. Keep following my YouTube channel. I appreciate your support, and I will talk to you next time. Adios.